How is everyone? Doing well, thank you. So, good morning. We are right on track, actually, a little maybe ahead of track. That's always good. Today, we're going to look at ways of counting larger numbers and such, larger groups of things. And um, for part of it, we're adding, for part of it, we're multiplying. And just think about it. When you're counting, you're basically adding one more, right? So most counting is based on adding. Or I've got two, three over here and two over here, I get five. So that's one way of counting. But when we get large groups of things that are repetitive, we start using multiplication because multiplication is actually repeated addition. So that's how it's going to be. So we're going to talk about that today, come up with a couple of different methods, and we'll be finished pretty quick. We're also going to use a couple of features on our calculators, again, going along with what we did with the matrix. So everything we can do, we can pretty much do it with the calculator, but we just have to know what type of counting we're doing. We've got spring break coming up, so that's going to be a good opportunity to get caught up on anything that you haven't done yet. Also, a good time to take a break. That's what spring break's about, right? But at the same time, if you can make sure you're on track, what I want to point out is actually last week, these three are really the same types of problems, right? We got it down. We didn't go into Kramer's rule pretty much because it was just a complicated way to do the same thing we could do with either 4.2, the reduced row echelon form, or with the matrix inversion. Those were really two different methods to do the same thing, to solve an equation, to solve multiple systems of equations. So those really all go together. So once you get it down, you're going to be fine. And so then there's really just two, the matrix and the matrix operations. So, but you got to kind of understand those to be able to do the others. And again, a lot of it we can do with the technology, with either the TI-84 calculator. And one of your colleagues did actually went out and bought that NumWorks that I spoke about for $99. I hadn't ever seen one, but it's pretty nice for 99 bucks. Came to him right away. He got it through Amazon. So if you don't have one, and he said it took a little bit of learning curve, but it's a lot easier to do matrices than even the TI-84 because it's got all the things right there. And again, you can, if you want to test it out first, download it to your phone or tablet, and it's free. You test it out, play with it a bit, and once you get it, it'll be basically the same thing, but now it'll have buttons instead of touching a screen. So, but that's, again, it's really, this class is technology heavy. In fact, when I teach it at the community college, it's got that word technology in it. And the goal is to get you to learn how to use the technology. They use actually spreadsheets. They use a little bit more stuff than we do here, but that's what we're going to do. When we come back from spring break, just to kind of prepare you, we're just doing basically two types of probability and then probability and counting. So things like calculating the probability of a lottery, like a Powerball or something. How do we do that? We combine what we're learning today with a little bit of the probability, and we can do it all. Okay. And then we got a couple days, basically a whole week to get ready for it and then take the test. So I just want to remind you that in the last module I have there is this review. If you are caught up or as you get caught up, it'd be good to kind of review this, go through it. I'm going to do that over spring break too, maybe earlier part of spring break. I'll make videos of all of these so that those are ready to go. So these are the ones on matrices, Gauss-Jordan reduction. So some of the harder part without the technology is getting things set up, but we've got, some practice problems to do. And then that's all matrices. So that's all we've already done. And then here's what we're doing this week. Maybe dive into that after you get through there, and then you're ready to go. But anyway, I'll work on that too. Look at a few things every day, and you'll be amazed at how far you can get without having to like give a whole day of your breakaway. Maybe just 30 minutes. Take a quick look, focus and do it. But by doing that, you're learning over time. And even if you don't do something, a lot of times what I do, I just read it and then I'm thinking about it and it's in the back burner. And then when I come back to it, sometimes my back burner is smarter than my front burner. So it's like it gets it solved and they go, oh, how did I do that? So, but just keep in touch with things. The hardest thing is if you lose contact, you don't do anything for a week, then you come back and it's all fresh again, right? It's all new stuff. But if each day you do a little bit, keeps you going. Same thing with like exercise. That's what my friends tell me. I don't always do that every day either. But anyway, that's where we're at. So today we are going to get into this, they call it decision algorithms. Again, they use a lot of sort of big fancy words that they've made up with we've got stuff to choose from. Going to go to a ice cream store, get to choose our favorite flavor. How many different types could we get? Those kind of things. And we're going to see sometimes we're adding the choices, sometimes we're multiplying them, and part of it is deciding when do we add and when do we multiply. That's really all this is about as we make decisions. Okay, so addition and multiplication principles. So going to lunch, and we're going to have just one dish. We have a list on a menu. There are 8 chicken dishes, 10 beef dishes, 4 seafood, 12 vegetarian. How many different choices do we have? Now you said in reality, right? Some of us, maybe we don't eat beef, or maybe we don't like seafood. So those really aren't choices for us, but the person who maybe would choose any of these, which ones, right? How many choices do we have? Well, how many, so when we do these types of things, we think is how many choices are we going to make? How many meals are we going to order? One. Unless we're really hungry, maybe we order, but you order one. If you're still hungry, order another. That's but don't order both of them because you think you're hungry, because you'll get filled up and go, why did I order this thing? And then you eat it anyway. Okay, yeah, I'm talking about myself, and you get too full. Anyway, one thing. So certainly we could think of it, if they just had the 8 chicken, I have 8 things to choose from, right? If they add another menu that has 10 beef things, how many more choices do I have? 10 more. So it really is as simple as 8 plus 10. And again, because these are additive, these are just more choices to make. We're going to see that the multiplication comes in differently. So I've got 8 plus 10 plus 4 plus 12. We've got, if we add them all together, there's 20, and 14 is 34. Did I get that right? Good. Okay, thanks for verifying. So there we are. We have 34 different meals we could eat. We could order. Right? That's it. But as we go through, what we're going to see is now we're going to go to lunch, and we're going to get fancy lunch. We're going to get an appetizer. We're going to get a meal. We're going to get a dessert. Then that changes things because we've got multiple choices. Multiple choices, multiplication, right? So that's kind of easy to remember there. So here, 34 different possible lunch orders. If we're just ordering one thing, so that there's really one choice to make out of a collection, and the more they have, we just add them together. Make sense? Okay. And again, it's the hardest part of all this stuff is it seems like they try to make it hard with different vocabulary stuff. But if 34 things on the menu, I've got 34 choices. That's really all it is. Let's see. Now, we'd like an appetizer because we're going to dinner, and a main dish, and a dessert. I'd like a drink too, but maybe, okay, they didn't give us that option. So how many choices do we get to make as we lay out our 3-course meal? I sort of said it, right? 3 choices, 3 courses. We get to choose each one of those. So I like to this is my technique. I put 3 lines. I'm going to make 3 choices, right? And what I'm going to choose an appetizer. I'm going to choose a main. and I'm going to choose a dessert. So for my appetizer, how many different choices do I have? 5. So I could choose 5 different things. We're going to see how we can also do this, but so I make one of those choices, but I have 5 choices, and depending upon which one I make, basically you could think of it, you've got, if you, we'll look at a tree diagram, but from those 5 choices, each of those now have sort of branches coming off. How many choices do I have for my main dish? 34. And so for each of the appetizers I made, I could have 34 different main dishes. So it's really a 5 times 34 is what I'm doing here. It's not additive here because I've got 3 different. So each time I make a choice, I'm really multiplying the different combinations. Okay, so we're going to multiply. And then desserts, there's 10 of those. So this is the multiplication part. So it's as I get how many choices I don't know how to say this right maybe, but how many things I'm going to choose, how many different decisions, I'm going to make 3 different decisions, each of those get multiplied. Remember last time, I was really only making one decision from 34 different things. This must be the same menu, and then they got the appetizer. But now I'm making 3 different choices. So as I make one choice, I've got 34 coming off of those, but I could have made a different choice and there would be 34 different. So each one of these is different. And you multiply that out, that's 300. Let's see, 5 times 10 is 50. That is 20 with a 0 on it, and 15, I think, 15,200 or 15,200. Did I get that right? 17, I probably forgot to carry something. Yeah, 15. Oh, probably had to carry the 2. See, that's why I don't trust myself. Okay, 15,000 even. 17,000 even, because that 2 got carried. Okay, 17,000. So that I gotta make 17 or 1,700. Okay, see, I forget. I'm just trying to make it easy on myself. Actually, I'm being lazy, and that's where the problems come in, right? Okay, so thank you. Just plug it in. 17,000. That says I could live with 170, 100, 1,700. I can't even say. Sorry. Okay, let me go back to sleep and come back. Okay, 1,700 different choices from that menu. Wow, that's like too much. But you see how you can advertise. We've got 1,700 different meals for you. Wow, that sounds like a lot of variety. I want to go that place. It's just a matter of having desserts. And now, if we threw in the drinks, we could have even more, right? If I had like 15 different drinks, this would be multiplied by 15, and then I'm getting big. So, but that's how these things work, is how many choices do I have? How many decisions am I going to make? Those always get multiplied. I take from whatever it is, and again, if I'm just making like one decision, but from several different options, that's when I add. Okay. All right, good. And then use the calculator. That's the main thing, is otherwise you just kind of, so easy to make a mental slip or try to do it that way. So, or just push the button and it'll give you the answer, right? So, but anyway, that's why I like to do it, is so you can kind of see when you make a mistake, what should you do? Or it's like I said, I'm making mistakes all the time, so I always have to find ways to check them. Yeah, 70,000 sounded like way too many. Okay, so here's another longer one. So we'll kind of just get an example working through a longer word one. But again, it's really, we're either going to add things or we're going to multiply things. So you walk into an ice cream parlor for dessert and decide you want either an ice cream cone or a yogurt, cup of yogurt. So are we going to get both? No, we're only getting one. So we're getting one thing. So I'm going to need just kind of like one line. I'm only going to get one thing, but I got these 2 different things. So the ice cream comes in 15 flavors, the yogurt in 5, and then you can choose among 3 different sizes of cones for the ice cream, or 2 different cup sizes for the yogurt. Okay, how many different possible options for this dessert are there? Okay, so again, really we're only going to get one dessert, but the thinking is, let's see, if I was going to get ice cream, How many choices do I have for my ice cream? How many decisions am I going to make if I go for the ice cream? 2, I'm going to decide flavor and size, right? Small, medium, large. Always go for the large. It's usually the best deal, right? And you can always throw it away if you don't need it or give it to somebody, but if you got the small and you're still hungry, there's, it's just my choice. So ice cream, we got 2 choices. We've got 15 flavors, and then we've got 3 different sizes. So that's a 15 times 3, right? Because for each flavor, I got 3 things. I could do the small, medium, large. Each flavor, small, medium, large. So think of it as 15 times 3. Okay, so that's the total of choices there. And I might be able to do this. That's going to be 30 plus 15, 45. Okay, see, small numbers I'm okay with, but try to get me 3. So the ice cream, I'm going to have 45 different choices. So I look at that. Well, maybe I heard yogurt's a little healthier. Maybe I should go that route. How many choices do I get with the yogurt? So the yogurt, I've got, again, still 2 choices, still two decisions to make, right? I got the flavor and then the size. How many flavors do we have? Got 5, and we've got 2 sizes. And so that's going to give us 10 different distinct desserts we could get there. Then what do? We take 45 times 10, or do we take 45 plus 10? What's that? Times or plus? How many say plus? A couple of you. How many say times? Okay. How many decisions are we going to make? We're only going to get 1. So here's the first. So we make the decision. We're either going to get ice cream or yogurt, right? Ice cream or yogurt. So if we do get the ice cream, we've got 45. If we get the yogurt, we've got 10. If we were going to get both of them, then we would multiply. If we were going to get 2, first decision times the second decision. But since we're getting a 1, we still have sort of a decision to make here, right? But once we make a decision, we've only got that many. So really what we're doing is we're choosing between 55 different choices. It's almost like if this was all laid out on a menu, we're really only going to choose 1 of them. Okay, so this is the hardest part, is sort of deciding, do I multiply or do I add? And so in this case, there's a 45 plus 10, because we're not getting 2, we're only getting 1. So it's like these are all the choices I have. That's additive. Oops, 55. So they say we're going to get an ice cream, right? Oh, I've already got my work up here. It's like on the test, right? You write it someplace else. You go, oh, it's supposed to go there. Just put arrows. Look over here. Okay. You don't have to rewrite it. There it is. And then the last one, this is what's called a decision algorithm. Okay. And then the last part probably was here. We need to add them together. Okay. So that's the whole structure of the thing. We're getting 1 thing. So these are all the choices. But within each of these, since I make a choice and then I make a second choice, right? Size, flavor, and size, those are multiplied. And we're going to see why that is with the sort of the tree diagram with something a little simpler. So far, are we okay? Nobody wants to shake their head, right? Not really sure, so I'll just be quiet. That's how it is. Okay, now this one, we'll look at this. So getting dressed in the morning, going out to the gym. You can choose between 2 t-shirts. You've got a white one and a gray one. 3 pairs of shorts. 2 shirts, 3 pairs of shorts. We got white, green, and blue. You better wear some tennis shoes too, but they didn't give us that choice, so I guess we only got 1 pair of tennis shoes maybe. But the first step is we need to select a t-shirt, right? Oh, they're supposed to come in slowly, but anyway, we've got 2 choices on the t-shirt, 3 choices on the shorts, so that gives us not 16, just 6. I don't know where the 16 came from. Just 6. 3 times 2. 2 times 3 is 6. 6 different outfits. We could look different. The white shirt with the 3 different colors, the gray shirt with the 3 different shorts. Not all at the same time, but yeah. So we could have 6 different looks. Does that make sense? Again, and it comes down to we're multiplying because we actually have 2 different decisions to make, right? The shirt is one decision. The shorts are another decision. And as we make one. Now this is where I think it's next. We could do it with the decision tree. And so this will help you visualize. Move this all out of the way. You can see the first decision, we have 2 things to decide from. And for each of those decisions, we have 3 different options coming off. So you could count, we've got 6 here, or we could think of it as 2 times 3, right? Gives us that 6. And so those would be all the options. We'd have the white shirt with white shorts, green. So that's 3 options. We go with the t-shirt, the gray shirt. We got these 3 options. So we could do this decision tree, I guess they call it, tree decision, whatever. But it doesn't work very well if you got 20 options. How do you draw all these little fingers? But it's good for a conceptual look at things, right? So most things is each time you have to make a choice, then it's a multiplying type option. And if we had different kinds of shoes, we could come off of here. And so each of these outfits, so white and white with the red shoes or the brown shoes or the black shoes, whatever, so we'd have those options coming off here. And you could see, boom, boom, it would just get messy. But we can think of it, it's a multiplicative process because we're branching out. Each time we make a decision, we've got so many decisions to make. Okay. And again, a lot of this is just once we pick it up, we're just reading the problem and, okay, this is multiplication, just multiply. We don't draw it out. We don't have to do too much. Oh, I'm making one decision from a couple different choices. I just add those choices together and make it all together. Okay. So this was, I put this one in here. I left it in here because it's similar to, I looked over the homework and stuff, and it's the language they're using. Okay, so we'll read through. So we're taking an exam. It's broken into 2 parts. We have an A part and a B part. We're required to do both parts, so we're supposed to do A and B, right? So when we get those, are we going to multiply or are we going to add them? We're going to multiply because they're both required, so they're sort of like 2 separate things, but they have to be done a first and a second part. But for part A, we get to choose between either answering 10 true-false questions or answering 4 multiple choice questions. Now, they use the word and here, which really threw me, because and means you need to do both, right? They should have used or, at least in my way of thinking. But remember, in logic, and is sort of the backwards if we're thinking of unions. So maybe they're using log, but I had to highlight choose between. So we're not going to do both parts of the test. And the only way I did this is I looked at what their solutions was. Sometimes you cheat that way, right? You work backwards. You find out what the answer is, and then you go, okay, this is what they want. So, but that was confusing to me. So that's why I wanted to kind of leave it in here. Sometimes the book will use the word and. I would have used the word or. Okay. So for part A, I don't know. I can't remember if I have it step by step here, but part A, what do we do? Well, we either have 10 true, false, or we have 4 multiple choice. So we don't have to do both of them, just one or the other. So actually, we're going to add those 2 choices because we have either all of these or all of these. We'll do one or the other. So 10 true, false questions, right? We're going to do 10 of them. So we think of it this way. 10, I'll stop here, but there would be 10 of them. I'll go dot, 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 right? How many choices do we have for each question? True, false, 2. So I have 2 choices for this first one, 2 choices for the second, 2 choices for the third, and so forth. So how many times am I going to do that? 10 times, so that's 2 to the 10. So you'll see some of these problems where that's all it is how many choices is going to give us the exponent. So there's 10 questions, 2 questions each, 2 to the 10th. Phone numbers. How many different phone numbers can I make from something, right? You have actually 10 digits because you got 0 through 9. So that's 10 digits for 10 choices for each digit. So that's actually 10 to the whatever power, so we can do that too. So that's for the true false. How about for the multiple choice? Multiple choice, we're going to have, this is a little bit easier to do. There's only 4 choices, right? 4 questions, and each of them has 5 answers. So we have 5 choices for the first, 5 choices for the second, and so forth. So that's going to be 5 to the 4th power. This is for the multiple choice. And since we don't have to do both, we're going to do one or the other. This sort of gives us how many different exams we could do. We add these together. We don't multiply them. If we had to do both, we would multiply them, right? But so these are all the different types of answers we could have provided. 2 to the 10th is, I'm going to ask for someone to plug 1024. Yeah, okay, that makes sense. I knew it was something like that, but it's beyond my memory. I can go to 6 something. 5 to the 4th is 25. 125 times 625. Okay, it still sticks in there sometimes, but I needed verification. And so what I'm going to do is I'm going to add these two together. 1624 is basically how many different types of answers I could have provided. How many different collections of answers are possible? That's what the question is. So could have had 5 different answers here, right? For 4 questions. So that's all the different ways. Yes, sir. Oh, see, try to add correctly. Yes. Okay. Thank you. Thank you. Can't even add right. 2 and 2 is 4. And 4. How did I get that? I don't even know. I just half asleep at the wheel, I guess. Think 1649. Yeah. 4 and 5 is 9. I don't know what I was doing. So that's part A. Part B would do basically the same thing. So but we have a choice of answering 8 true or false, and then 5 multiple choice, which only have 4 answers to each. So again, it's going to be 2 times 2 times 2 for the true false, right? We're going to have 8 choices, so 2 times 2 times 2, 2 times itself 8 times. And then for the multiple, this is for the true false. For the multiple choice is 5. 1, 2, 3, 4, 5. Each time we have 4 different choices, A, B, C, D, right? 4, 4. So this is going to be 4 to the 5th, which will be a different number. And again, we get to choose between, we only have to do one of those parts. So it's just, we could do this one, which has that many options, this one that has that many options. So we add them together. This may be more for the teacher who has to grade them. These are all the different combinations. 2 to the 8th is 256. I was getting there, but slowly. And 4 to the 5th is 1024. And let's see if I can remember how to add correctly this time. 4 and 6 are 10. Now slow down. And that's one of the key parts is usually when you make mistakes, or at least you're going too fast. 5, 7, 8, 2, 1280. Okay. And so these are all the possible answers. There could be 6,649. I got the, for part A. Part B is this. And since we have to do both parts, right? Think of this as a decision, as a decision tree. Each, for each of these answers, there's this many coming off. Again, that's you can't really draw it, but we know we need to multiply these two. So we'll take our 1649 times 1280. Anyone else check all our numbers here? They look pretty good. And if we take 1649 times 1280, what do we get? Say it again. Something like that? Did I get it right? Okay. A lot of different possible answers. Okay. And sometimes, I mean, these are the types of things they use for like testing people, or they'll say how many, there's all these different ones, and then if you see the group has all the same answers, then you go, oh, maybe there was some collusion in here, or something like that. How many of those answers are going to be correct? You get 100%, there's really only one answer, right? Well, however many choices, so there's 10. Anyway, there's all that many ways to answer it, but there's really only one way to get 100% to get them all right. Okay, but see that counting, there's the difference between multiplying and adding. So adding is when we sort of have just one choice to make, but we're maybe have a couple menus to choose from, and we go there. I left this in there. I usually don't think about this, but it's just saying not all choices are valid. So going back to that getting dressed for the gym, what if we didn't have a gray t-shirt? What if we had 2 white shirts? Then would it really matter? Are these different? I don't know. I spill stuff on mine, so sometimes my white shirt has one stained and one's not. So they're different, but okay. So let's see. But if they're not, right? So they say that this is really not a valid 6 choices. It's really only 3 choices, because you would look the same. You have your white shirt and these, or you have your white shirt and these. These are really the same. So that kind of plays out in what we're going to talk about when we get to combinations. So I just sort of left it in there to say they could have something that there could be this possibility of not a valid choice. If you've got 2 of the same, it doesn't really matter if you use the one on the left or the one on the right. They really are the same. Okay, white t-shirt is white t-shirt. So that might come into it. All right, now we're on to the home stretch, and I'm going to actually, in 2 slides, I'll teach you everything you need to know, and then we'll just look at a couple examples. And this is the one where works really well when we're with our calculators. We've got a calculating thing in there. Okay, so this is permutations and combinations. They're very similar, but there's one thing different about them, and that's the thing that whether the ordering or the arranging of the items is important or not. Okay, so we've got things to choose from, and so I'm going to start off with, let's see. It is useful. So this is still making a decision, but when we're counting how many different ways there are to do something, we could either have a permutation or a combination. With a permutation, order matters. Order is important. The arrangement is important. So I'm going to do it with like arranging books on a shelf. If I change the arrangement of those books, it looks different, right? If you're in a library and you change them, you might not be able to find the one because they're supposed to be in a particular order, right? These ones maybe are not a particular order, but I'm like, oh, that's pleasing. Or maybe I want to have all the sort of similar color ones together. Maybe that's how I want to do it. So there's different ways I could arrange this, and each one is different. If I even just taking this last book and moving it to the front, it's now a different arrangement, right? It looks different. So that's a permutation, and we're going to see how to do that. But I could also take those same group of books, and I need to ship them off to a friend, and I put them in a box. So the order of that I have them in the box is not really important, because the friend gets them and he dumps them out on the table anyway. So whatever order I put them in there, it doesn't matter. So something like and we call that a combination. And we'll see that the ways of calculating those are different. So my friend got her books. She brings them out of the box. Whatever order I had them in, Doesn't matter because she got them all, right? If I put them on a shelf and arrange them, order is important. Okay, so and we're just going to look at the calculations are very similar, but a little different. Okay, a little different. Okay, so we're going to first look at putting books on a bookshelf. Two different things. We have 7 books to choose from to make a display on a long shelf. How many different displays can we make? So let's go back to what we were just talking about. We have 7 decisions, right? We got to decide which one we're going to put on the first one, which one on the second, third, fourth, fifth, sixth, seventh. We got our books. We're going to go put one on the shelf. How many choices do we have for that first slot on the shelf? 7 choices. We put one book up there. How many do we have in our hand? 6. So we see this. It's going to be easy, sort of. So now we only have 6 choices. And then we put one on the shelf and we only have how many in our hand? 5. And then we have 4 because we put one on the shelf. And then we have 3 because we put one on the shelf, 2, and then we have 1. And these are separate decisions that we had to make each time. So it's a multiplication problem. We multiply these all together, and that will tell us how many different arrangements we could have made. Okay. And what's this, 540 or what? If I multiply all those, yeah, I usually use 7, so it's just over the years I've got to know that when 7 times 6 times 5 times 4 is 540. Mathematically, we call this 7 factorial and use the exclamation point. So and actually I'll show you on the calculator, we have this, so if you need to use it, you could do that. It just knows to take 7 times 6 times 5 times 4 times 3 times 1. You do 99 factorial, 99 times 98 times all the way down. So it's kind of a nice key to have, but you can see if we get very large, we're going to get, the numbers get really large, right? 10 factorial is 10 times 9 times 8 times 7 times 6. Yes? 5, okay, yeah, 5,040. I missed a 0 in there. Yeah, a lot bigger. 5,040 different arrangements. So if you wanted to kind of just, change a book a day or something, you could for 5,000 days, 5,040 days, you could have a different arrangement. And then you would start to repeat it somehow. Okay. Do this as a batting order or something on a team. How many different batting orders could you have, right? Depends on how many are up and all those kind of things. So this is but this is, again, the key part of this is this only works when order is important. We'll see, we'll start with this with the other one, but we'll go. Now, what if we had a short bookshelf and we can only get 4 books on there? How's that going to work? 1, 2, 3, 4. Well, how many choices do I have for that first slot? I still have the 7 books, but I put one on there. Now I've only got 6. Then I've only got 5, and I got 4. What do I do with the other 3? Put them in the closet. So there's one thing or whatever, I don't know, take them home. But nothing, so we're done here. How many choices are there here? 7 times 6 times 5 times 4. 840 now. So fewer choices, obviously, as we've done that. What I want to do is I'll show you the formula for doing this. But you can also do it, I usually will do it sort of this way, just how many choices am I making, and I just do the countdown. There is a formula. We could, starting with 7 factorial, how do I want to do this? Let me do it this way. Change colors. So what we would do is if we could put all 7 books, we'd have 3 times 2 times 1, right? But we don't have places for the last 3 books, so what we do is we're going to divide by 3 times 2 times 1. And notice those sort of just cancel out, right? So that's sort of the formula way that it works. So we call this a permutation. We've got 7 books to choose from. We're only going to use 4 of them. And so the way we calculate this is we say, okay, that's going to be 7 factorial over 7 minus 4 factorial, because we're only going to use 4 of them, right? 7 minus 4 is actually 3. And that's what we have here. This was 3 factorial. So you're going to see this in general. They will use the letter N for the number of choices we have, the 7 books, and they'll use R for the number that we have spaces for. So you'll see on the calculator NPR, not National Public Radio, but N choices. Permutation means order is important, and that's how many choices we're going to get. Okay, and I'll show you on your calculator. If you go to your math key, and this is, you're going to see, deals with probability. And there it is, NPR. So I'm going to pull it up, hit enter, and then I just put it in. 7, choose 4. 840. I could have used it for that other one as well. Oh, not just, it's not shifted. It's just the math key. Let's see, math key over to probability. Bless you. NPR. 7, choose 7. 7, use 7, or 5,040. So we get that same number. So this is a little feature in here. You got a different, Casio will have it as well. Most calculators will have it. So we just need to find it, but it's a great feature to have. So far, so good. Okay, so we can do anything here. We're going to see that the combination, and you'll see right below it, right? There's NCR, that's for combination. So that's the other one. Again, so as long as you know, is order important or order not, we know which one to use. Let's just do this one first. What if order was not important and I had 7 books and I need to send 4 to my friend? How many different choices are there? A lot less. And we're going to see the mathematics behind it. We don't have to do the mathematics continually, but we'll see if combination, it's a lot less. But think about it, because it's a set of books that we're sending it, so the order is now no longer important. Okay. Heck, how do I, let's see, go here. There we go. So the visualizing it, order is important. So there's a first, second, third somehow. There's a arrangement, combination. They're in a box, they're in a bag. They'll get mixed around. It doesn't really matter what order they're in. They're just all 3 in the bag. Okay. And where's my other slide? I was supposed to have one more slide. Oh, well, I think I went through this. Oh, this must be after this. So to visualize this, if we have 3 letters, A, B, C, if we think the permutations, right, we could go A, B, B, A. So those are different. But if we were just looking at them as orders not important, AB and BA are the same thing, right? So these 2, there it is. These 2 are really just one thing if we think of it as a combination. And this AC and CA, these 2 are really just one thing, A and C, because order's now not important. If order's important, there's 2, B and C, or C or B are 2 different things. If order's not important, they're only one thing. Okay, so what you're seeing is when order's no longer important, when order was important, we had 6. When order's not important, since we're organizing 2 things, we divide by 2 factorial. And so then there's really only 3 things in the combination. So that's, we're going to divide out how many different arrangements we're doing. Okay. So again, we can use that, but 7 books, choose 4. It's the same thing as the permutation, right? So we do 7 factorial over 3 factorial, right? Because that's the permutation. 7 minus 4. I'll do it this way, 7 minus 4. But then since it's a combination, what we're dividing out is, since we're arranging 4 things, that's 4 factorial ways to arrange them, but each of those arrangements is really the same. You do this book first, second, third. It doesn't matter which order it is. So we're going to divide out the number of ways to organize it. And so, the mathematics behind this is a little messy, 7 factorial over 3 factorial, 4 factorial. Doing it by hand is not really important. We just use this, 7 choose 4. It has that formula built in, and you're fine. There's nothing, but you could, if you want to, write out 7 factorial, right? You could go 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 3 times 2 times 1 times 4 times 3 times 2 times 1. And you can see this part cancels out. So this is the permutation on the top. Oh, and then we can cancel 4. We can cancel 3 times 2 is 6. So we can cancel that and divide by 1. So 7 times 5, that is 35. And when we put this in our calculator, we got 35. So our calculator handles it all for us. We can go through sort of the macho way of doing it. I'm strong, I can do the math, but it's a lot of tedious work, right? We can also just use the technology and it will do it. But I want you to understand what all we're doing is we're taking a permutation and we're dividing out the order. Okay. So if I was going to send all 7 books, how many different ways can I do that? One way, actually, right? 7 factorial divided by 7 factorial, pretty much. I'm sending them all. They're all going to go in the box. There's one way to do that. Okay. And you'll see that if you do a 7 choose 7, you'll always get 1. You always get 1. So you can play with it. But that, again, technology. Technology. And that's basically all you need to know. The thing is coming up when deciding whether order is important or it's not. Now, let me just throw a few at you. If I need to choose, if I was making a playlist for my for songs, and I had 10 songs to choose from, maybe I'm having a graduation, whatever, and I want to have these songs playing. I have 10 songs to choose from, but I'm only going to use 3 of them. Is that order important or not important? Do the songs just kind of go into a box where that doesn't matter, or is there going to be a first song, a second song, a third song? It's one that always gets me because I think order's not really important, but it is, because there is a first song, a second song. And think about it, when you listen to music, some music will get you more excited than others, so it will make a different experience depending upon the order that we play the songs. But it always gets me, it's not really important, but it is. It is, because you're not going to play them all at the same time, hopefully. Yeah, so there's a first, second. Whenever there's an ordering, first, second, third. I'm running a race, and there's a gold medal, silver medal, a bronze medal. How many, is that order important or not important? Yes. But if it's a race where the top 3 go to the next race, doesn't matter whether you score 3rd or 1st, you're going to the next race. Order is not important. So it's kind of like, it's just take some practice and thinking of it. And the cool part is you usually get more than one choice. So if you get it wrong, it just means, oh, order's important. Okay. And then just look at it and say, why was order important there when I thought it wasn't, or the other way around. Okay. But that's basically it. You got all the tools to do whatever you need to do. Let me just click through these. I think, so these were, here's a visualization. Order's important because you could actually, how you put the colors on a flag make for a different flag. 3 colors on a flag, 3 times 2 times 1, 6 possibilities. So there's a visualization there. This gets through all the 5 factorial, 4 factorial. Here's the formula. So it's just more a formalized way that we talked about. But again, it's just what we did. And I with that one particular example, that's the same thing. So those are there. And then combinations, the only thing is it's unordered or order is not important. And so it's the same sort of thing. But basically, this was the formula for, let's see, I should do it over here. This part here was the formula for the permutation. And this, we're just dividing out the different ways of ordering it. But again, just use the calculator's thing and it will take care of it. Sometimes I'll do both of them and I'll say, oh, which one feels better? One's going to be bigger, right? Permutation is always going to be bigger because that's order is important. The other one's going to be smaller, and try to figure it out. And again, if you got it wrong, you got another choice. And so you've got your two numbers, one or the other. It's always, that's the decision to make. And just more examples, you can work them out. They call it the binomial coefficient, but who cares? I got two things I can do, basically order is important or not. And again, what we're using this for is we're going to use it for when we get further down the road into probability. Like with a lottery, does it matter the order you choose the lottery numbers? Usually not, actually. Powerball, because if you choose 15, it doesn't matter whether you chose it first or second. It's just as long as you match. In Powerball, it doesn't. There are some games where the order of the numbers you choose is also important. It's like a trifecta if you do horse racing or something. So we'll talk about those. So that's where all this is leading us, gambling, which we shouldn't do anyway, because when you gamble, it's the casino that gets all the money, right? Some people win, but usually not me. Okay. Have a good weekend. Every Friday's an open work day, so come if you like. Thank you. Thank you.